All right. It seems that I'm the last one, so I guess I can go as much as I want. There are no limits. Well, I hope it's going to be fun, and I hope you're going to have the last level of concentration. So, my name is Alen Stojanov. I will be presenting a project where we trade compute for data movement in order to implement fast quantized arithmetics on x86. So this project is done with collaboration with Tyler Smith and Markus Kuschel, all of us from ETH Zurich, as well as Dan Alistar from IST Austria. So let's jump into it. What is quantization? Well, I'm pretty sure this community knows this very well, mapping input values from a larger set to a smaller set. In reality, quantization is lowering precision, and if you perceive this in terms of hardware, you can see how we can map values from a 32-bit floating point down to a 4-bit, say 4-bit value. Right? Technically, this means that with quantization, we can also lower bits used to represent the numbers, and that would mean we can actually have less data. Less data is important, and in the context of processing any kind of data that might be stored, say, in the RAM or any other cache hierarchy on the memory, if we reduce the data, we might actually save time. So this implies that less data will usually imply faster computations. So this was the reason why low precision computations become very popular, right? Compressive sensing proven to converge as little as 1 bit. The same applies for gradient descent. We have seen this on the previous talks. The keynote speaker, the first keynote speaker mentioned about TensorFlow. It can go all the way down to 4 bits, and we can have very interesting application like in the field of tomography, where we can reconstruct human torso with 12 bits instead of 32 bits, and so on and so forth. Now, I'd like to impose the question: can we do this efficiently on x86? So, what are the options so far? I mean, obviously, 32-bit instructions are supported natively. So we have instruction and computations. We have 16-bit that are supported starting from Ivy Bridge and beyond. But the thing is, like computations are not there, only conversion between the different formats, 32-bit and 16-bit. If we go to 8-bit, we know that the work of Christopher Dessau, also the keynote speaker, that 8-bit can be used to implement stochastic gradient descent efficiently on x86. But what happens if you go down to something even lower, say 4-bit? Well, maybe we can start looking for the answer basically in the same work of Christopher Dessau. The paper was called Understanding Optimizing Asynchronous Low Precision Stochastic Gradient Descent. It's a very nice work. I highly recommend it. But there was one part where it says that 4-bit stochastic gradient descent will be infeasible because ABX will lack 4-bit instructions. So we read that, and we dare to disagree. So, I mean, it's true that x86 does not have native support for 4-bit. This is obvious. But it is feasible to implement 4-bit computations by using 8-bit instructions, or 16-bit or 32-bit. The real question is, will they run twice as faster than 8-bit, and will they fit the hypothetical model proposed by this paper? So what's the challenge if you go down to 4 bits? Well, if we are lowering the memory, right, when we are processing at the CPU, we will have to pack and unpack or unzip these values, and then the time will go up. And the real question is, will the overall time be higher or lower when we use this? But let's think of in terms of gradient descent and just try to analyze what kind of computations we need. So if we take gradient descent, which is kind of simplified form of stochastic gradient descent, or another example from compressive sensing, namely iterative hard thresholding, we can see that those two algorithms are very similar. They are both minimizations, and they all work in iteration. And in each iteration, we observe that we can find routines such as matrix vector multiplication, or MVO for short, and we can find routines such as scalenat, or in terms of BLAST terminology, XPy routine. So if we want to try these experiments on 4 bits on x86, we have several requirements. We need as fast as computation to create conversions from 32-bit down to the lower bits. We need dot because we could implement matrix vector multiplication with dot and an AXPAR routine. We will be focusing on large data sets because all the application of ML do indeed focus on large models. And what we have on disposal is an existing instruction set. We have data parallelism through SIMD instructions, and of course we have thread-level parallelism with multi-core CPUs, right? But before we go to multi-cores, we really want to have the fastest single-core implementation. So let's start. Like, how do we quantize down to 4 bits? Well, the answer is we use stochastic quantization. What does that mean? Well, consider that we have a range, and we consider that we have a certain vector within this larger range. We can compute a scaling factor looking at the maximum absolute number, and then we can simply scale all these numbers. But since we want to go to 4 bits, we will need integers, so we have to perform rounding. And since we have stochastic quantization, we do a stochastic rounding by adding a random number picked from a uniform distribution. Once we have all that, we will round either the first or the second boundary, and this is how the computation will look like. So what do we know from here? We know that if you want to represent this in memory, we will need some way to store signed values, and we might need to store the scale, right? So let's go into it. So if we want to design memory layout, obviously we can represent the 4-bit array, simple as array, and we can represent the scale as a scale, right? But in reality, the interesting part is that since on x86 we don't have 4-bit memory addressing, we have to use 8-bit representation to represent this array, and for the scale we can use just 32-bit floating point numbers, right? But there is an interesting thing, like we don't really have to have one large array with a single scale. Instead, we can just subdivide the array into smaller blocks. And instead of having one scale, we can have multiple scales, each of them corresponding to the block that we are computing on. Now, each of these blocks, we decide to block the whole array into 64 elements. So 64 elements times 4-bit, it's 256 bits. And each of these 64 elements, since it has to be signed, is going to be a 4-bit nibble, which will have a 2's complement representation, so signed bit and value bits. The choice of 64 is strategic because 256 corresponds to a single AVX register, and this is why we made this decision. This is how it will look like in memory, and the vectors in memory. And when we want to represent matrices, we do the same thing, but instead of blocking in one direction, we go in both directions, essentially creating tiles of 64. There's 64 elements. Now, since we cannot really address these locations, what we have to do is find a way how we can extract easily a nibble from a larger chunk, right? And for that we devised fast packing and unpacking routine. So let me demonstrate how interfacing with 4-bit and 32-bit chunks would look like. So if we have a 32-bit chunks of memory where a certain nibble is located, we can just shift it to the left while shifting in zeros, and we can also shift it to the right such that we shift with signed bits. Now the value, the nibble, will actually reside in a 32-bit chunk with the sign maintained on the right spot. We can also reverse the same procedure, and we call this packing, when we want to take a 32-bit chunk that contains a 4-bit value and position it to the right spot. So we do exactly the same thing, logical left shift and then logical right shift. So logical right shift will shift in zeros while the other one shifts in right bits. So this is a very interesting technique because it's super cheap. I mean, shifts take only one cycle, and basically positioning and depositioning will happen in only 2 cycles of execution. So once we have that, now we want to see how we can perform the whole quantization process. Well, what we can do is that since we deal with AVX, we can just load 64 values with SIMDs, and this will take only 8 registers. We can find the scale and scale the whole thing. We can essentially we're going to get 64 floats in a nice range, and then we can just generate a randomness with an XOR shift algorithm. Then we add everything together. We convert it into integers, and essentially here we end up with 64 integers within the range of -7 and 7. Now, what we can do is that we use this fast packing and unpacking. So each of these nibbles will be positioned to the right locations. Then we can just perform a bitwise over reduction, and essentially we have packed 64 4-bit elements into a single AVX register. Now once we have done the memory layout, the next question is, how can we do the basic computations that I mentioned before, like dot, xpi, and MVM? Well, let's look at xpi. So at dot. So imagine that we have one block with 64 elements from one array and another block from the other one. What we can do is that we can just call an AND operator, basically extracting only the high 4 bits, and we can also perform a shift to extract the low 4 bits. We can do the same thing for the other array, essentially converting 4-bit elements into 2 registers of 8-bit elements. Then comes the interesting thing. We can take those two, and we can use this very nice instruction in x86, which is called, which does essentially multiply and add unsigned with byte. In reality, what it does is it's going to take corresponding element, multiply them, and add neighboring elements together and fill in 16-bit chunks. The only trick is that the first operand must be unsigned while the second one must be signed. To do that, we just transfer the sign from the first one to the other, and we just simply perform the multiplication and addition here, essentially obtaining 16-bit chunks. We can do exactly the same thing for the other array, and essentially we are operating in 16-bit chunk mode. We perform addition on both, obtaining 16-bit chunks, and then the same instruction that we use here can be applied to 16-bit chunks to obtain 32-bit chunks. Once we have that, we simply convert to float, we multiply with the scale and accumulate it in a single FMA. How does the whole kernel look like? I mean, this is basically the code. It's a rather simplified version, and it does a very good job, actually. Now, let's go to see how XP can be done. So for XP, there is not much we can do because scales of 2 blocks might be very different. So what we simply do is like we convert back to 32-bit floating point precision, we perform the addition, and we re-quantize again. If we look at MVM, matrix vector multiplication, not so much magic. Since everything is blocked, we just go tile by tile for the matrix with a single block of the array, and we just perform dot product, and we accumulate. On top of that, we can parallelize the whole thing. We use OpenMP to do the job. All these operations are invariably parallel, so this is super easy. We keep the CPU busy with prefetching. We implement a bunch of other routines required, like transpose, thresholding, accumulation, and so on. And the most important one, which we skip for this presentation, is that we also can do mixed precision, making sure that the MVM and the xpi can interface with 4-bit and 8-bit elements. And now comes to the interesting part: what are the results? So just a quick setup for the result. We're testing 32-bit, 16-bit, 8-bit, and 4-bit. There are not so many differences, in fact, except that 8-bit and 4-bit undergo stochastic quantization. This one, the 32-bit, does not get any stochastic quantization, or no quantization at all. And the 16-bit, we use the hardware to perform the conversion. And only the 4-bit version is fully handwritten, while we use Intel MCAL to perform matrix vector multiplication, as it is a well-known implementation and probably the fastest out there. Now, this is how a dot product would look like. We test our results on an Intel Xeon machine, which is actually a Haskell machine. We turn off hyperthreading and turbo boost, so we don't have problems with measurements. We use Intel compiler 2017 with MCAL and IVP. And note that the maximum theoretical bandwidth, according to the documentation of Intel, is on this CPU is 25.6 gigabits. Now, here is the result of the dot. On the x-axis is the size of the vector, while on the y-axis we have measuring flops per cycle. So obviously higher is better. So what we can observe is that in the cache hierarchies, say the 4-bit does not really win against all the implementation. And this is because of the overhead that we have to undergo with packing and unpacking the data. But once we exit the cache hierarchy, we can clearly see that the 4-bit version clearly wins against all other implementations. What is also interesting to notice is that the bandwidth is still at around 15 gigabits per second, so that means that it's not being utilized. So if we parallelize, we will get even more. And this interesting trend we can observe in the XPi implementation. So if you see a single-threaded version, outside of the cache hierarchy is as fast as a 32-bit. However, it uses only 2.43 gigabits per second of the available bandwidth, while the 32-bit is almost exhausting it to 20 gigabits per second. That means that once we go to 4 threads, XPi at 4-bit and 8-bit will be a clear winner against the 32-bit or 16-bit implementation. A similar trend is also being explored with matrix vector multiplication. The only addition here is that we also added the mixed precision of 4 and 8 bits. So on one thread, we're still better, but not linearly better, and still underutilizing the bandwidth. Once we go to 4 threads, all implementation are exhausting the bandwidth, and we have a linear speed up. So 4 and the 4 and 8-bit will be 8 times faster than the 32-bit. The 8-bit will be 4 times faster, and 16-bit will be 2 times faster. So what happens with real life application, particularly the one that I mentioned before? So this was gradient descent and iterative high threshold. So in order to test that, we picked values of the inputs such that the conversion becomes slightly harder. We initialized everything with random data, and we used grid search for hyperparameter optimization for the mu parameter in both cases to decrease the error. And what we observe is that so we tested in 2 scenarios. And what we observe is that if we just go on average on 1,000 iterations, the results are basically inherited from the MPF because this operation is dominating the computation. So 2x, 4x, and 8x compared to 32. And this applies, of course, when the data is outside of the cache. But there is an interesting thing. Like if you lower precision, convergence does not happen at the same rate, and you might need different type of different count of iterations. So we wanted to see the absolute speed up on these computations, and in order to do that, for each problem size we found the minimum error that we will attain with 4 bits, and then we found the number of iterations to get there. So the computation is fair. And the results are very interesting again. So what you observe here is the size of the mix is the relative speed up with the 32-bit implementation of gradient descent. What we observe is that the mix 4 and 8-bit is almost 5 times faster than the 32-bit implementation. The 8-bit is about 4 times faster, and the 16-bit about 2 times faster. A very similar trend we also see in the compressive sensing test, where we are like up to 7.5 times faster with the 4-bit than 32-bit, about 4 times faster with 8-bit, and about 2 times faster with 16-bit. So we implemented everything, and we put it on GitHub. We named it Flower because it has 4 bits, so just like the flower, the plant. And turns out it was picked up on Hacker News. So we were there for like a whole day. It generated about 4,000 page views. Nobody complained, so we think the code works. So yeah, so you can try it out and test it and see what's going to happen and what kind of performance you can get. Yeah. So to summarize everything, what I presented was Clover, which is a new library for efficient computation for low precision data. We showed that 4-bit computations can be implemented efficiently on x86, even though there are no instructions there. And we focus on once the data resides outside of the cache hierarchy. And as a result of that, we have successfully traded compute for data movements. Thank you very much.